all aware that fashions change every year. And nowadays, they seem to change in the wake of every movie. But when you think about it, you realize that food habits change too. I mean, you could look up the sales statistics, but all you really have to do is wander down the aisles of a supermarket. You see products that just weren't here a few years ago. And you notice that some of the things that you used to like seem to have disappeared. An interesting case is fruit juices. I can remember when people only drank juice for breakfast or when they were sick, but now juice is a popular beverage anytime. One consequence is that juice companies have created new blends in the hopes of attracting more customers and garnering a larger market share. Here, for example, are some recent entries into the juice field: pineapple orange, apricot nectar, even tomato clam. One combination that seems to have caught on across the country is apple juice mixed with cranberry juice. At New England Apple Products, apple cranberry juice cocktail is only one of the 16 very fine beverages blended here. Steve Rouse is the manager of marketing.
The juice category includes apple juice, orange juice, and grapefruit juice, and also apple cranberry cocktail and a straight cranberry cocktail. And then we also have a group of fruit drinks that don't contain as large a percentage of pure juice. And those include fruit punch, grape drink, orange drink, pineapple orange drink, papaya punch, apple cherry berry drink, lemon lime drink, tea with lemon, lemonade, and a natural energy drink, which is an isotonic drink.
As you might have suspected, there's an important mathematical principle underlying the operations here. It all boils down to this, if you'll pardon the pun. If you work it very fine, there are a lot of possible products that you can make, but you need ingredients for all of them. So how do you decide which products to market and how much of each to make? Well, not surprisingly, the main criterion for determining certain production policies might be profits. If you make more money on a bottle of cranberry juice than you do on a same-size bottle of apple cranberry, your first inclination might be to give up apple cranberry altogether and make only cranberry juice. But hold on, you don't want to waste all the apple juice that's sitting in your vat. So the real question is actually a little different, and it's a basic management issue. What's the best product mix for you to make the greatest profit? And the question has to be addressed in a context we've already learned something about: constraints. In this case, the amount of raw materials, the berries available, puts a limit on how much you can make of anything. The problem of how best to use limited resources, such as berries, especially when there are a lot of possibilities, comes up in many settings. In mathematics, we call this process of making the best choice optimization, another term that we've come across before. Our juice example is typical of a category of management science problems called linear programming. The dollars and cents impact of our ability to recognize and solve linear programming problems is enormous. If you pick up a bottle of juice and you look at the list of ingredients, you won't find linear programming, but it's actually a kind of hidden ingredient. Let's find out how linear programming works by imagining that we're in charge of a highly simplified fruit juice manufacturing company. This use of simplification, of focusing on certain factors that we're interested in, is a familiar technique in mathematical modeling. Our modest little firm manufactures only two products: cranapple juice and appleberry juice. These juices are both composites of cranberry juice and apple juice. And in order to keep our model as simple as possible, we'll say that these are the only two ingredients. Cranapple juice differs from appleberry juice, therefore, in only one way: the recipe. Now, I'm going to depart from traditional business practice and reveal to you the secret recipes for these two products. You take 3 quarts of cranberry juice and 1 quart of apple juice, mix them together slowly, brew carefully, and you produce 1 gallon of cranapple. For appleberry, the mixture is different. 2 quarts of cranberry juice and 2 quarts of apple juice make up 1 gallon of appleberry juice. Now let's get to the core of our problem: determining what production policy we should follow. In our model, that means figuring out just how much cranapple juice and how much of the appleberry we should make, are two unknowns. Since we're new in the juice manufacturing game, we'll need to know a few more essential facts before we begin. First is knowing how much of the recipe ingredients are on hand. We have a 200-quart supply of cranberry juice and 100 quarts of apple juice. As we saw, it takes 3 quarts of cranberry juice and 1 quart of apple juice to make 1 gallon of cranapple. The profit we can make on our cranapple juice is 3 cents per gallon. What we still don't know is how many gallons of cranapple to make. We could take a wild guess, but what we really like is the optimal production policy. Linear programming will allow us to figure that out with just a bit of algebra. Start by calling the amount of cranapple juice to be made X. The recipe is a little different for appleberry. Mixing 2 quarts of cranberry with 2 quarts of apple yields 1 gallon of appleberry. Each gallon makes a 4-cent profit. We'll call our second unknown Y to represent how many gallons of appleberry juice to manufacture. Since the profit on cranapple is 3 cents, and we're planning to make X gallons, the profit on cranapple is 3 times X. Likewise, Y gallons of appleberry at 4 cents profit per gallon gives us a profit of 4 times Y on appleberry. The total profit, then, is the sum of the profits on both products, or 3X plus 4Y. It seems that the larger X and Y are, the larger the total profit will be. A good strategy might be to make billions and billions of gallons, and then we could reap enormous profits. Why not? Because we only have limited quantities of the raw ingredients available. Remember, with only 200 quarts of cranberry juice and 100 quarts of apple juice, it's going to take some recipe to make billions of gallons of cranapple and appleberry. So we have to find a way to incorporate these fixed quantities or constraints into our algebraic approach to the problem. What we need to do is to build the recipes into our formulas. Since it takes 3 quarts of cranberry and 1 quart of apple to make a gallon of cranapple, and I want to make X gallons, what I have to do is multiply the recipe by X. This means that total production will require 3 times X quarts of cranberry juice and 1 times X quarts of apple juice. The same logic applies to the formula for appleberry, and so I need to multiply this recipe by Y, the amount of appleberry I want to make. That tells me I'm going to need 2 times Y quarts of cranberry juice and 2 times Y quarts of apple juice. Now we get to the fun part. I'll pluck the cranberry requirements from both recipes and group them with our cranberry supply, which is 200. Then I'll do the same thing for our apple requirements. The resulting scheme here actually consists of 2 inequalities. One says that 3 times X plus 2 times Y is less than or equal to 200. The other says that 1 times X plus 2 times Y has to be less than or equal to 100. There are a couple of other inequalities I should add to our list. One is that X is greater than or equal to 0. Now, the logic of this is that we can't make a negative number less than 0 gallons of cranapple. And the same is true of appleberry. So we can also say that Y is greater than or equal to 0. These inequalities are also called constraints. So subject to these constraints, we want to pick values for X and Y that make our profit formula, and therefore our profit, come out as large as possible. But before we can think about how to make as much money as possible, we'd better address the question of how to find any values for X and Y that satisfy the constraints. Okay, I've talked about constraints and inequalities, but there's one more bit of terminology that we need to figure out a linear programming problem. We'll call any combination of values for X and Y that satisfies the constraints a feasible point. We'll call it a point because, as you'll see, we'll be representing it geometrically. If we collect all the feasible points that there are, we'll have what's called the feasible set. Now we can restate the problem we started with in true linear programming terms. We want to pick from this feasible set the point that has the highest profit. Stating the problem clearly, mathematicians always say, is half the battle. On the other hand, it's only half. Right now, we know the rules, but we still don't know how to find the optimal solution. In other words, we could pick the optimal feasible point from the feasible set if we only knew what the feasible set was. Let's create a map to search for our feasible set. You may recognize it from your high school days. It's called a Cartesian plane. We'll label the horizontal axis X to represent our unknown number of cranapple gallons, and we'll label the vertical axis Y for our unknown quantity of appleberry juice. Plotting our constraints will be the first order of this side of the juice business. Remember, our supply of the ingredient cranberry juice is limited to 200 quarts, and we'll need 3 quarts of cranberry for every gallon we make of cran-apple, what we've called X. We also need 2 quarts of cranberry to satisfy our 1-gallon appleberry recipe, which we've called Y. Now we're ready to plot our inequality, 3x plus 2y is less than or equal to 200, by drawing a line that separates the plane in two. On this side of the line, the points call for more cranberry juice than we have. All these points call for less than the 200 quarts we have, which means this yellow region represents the amounts of cran-apple and appleberry that could be made without requiring more cranberry juice than we have. The points that fall directly on this straight line, though, call for using exactly the amount of cranberry we have available. These are the points where instead of having an inequality, we can use the equal sign. So we can label this line as 3x plus 2y equals 200. It's a familiar expression, but we've replaced the inequality sign with an equal sign, making it a linear equation. This line then, the divider, indicates the points where there's exactly enough cranberry juice to carry out the maximum profit policy. I've basically been dealing with one constraint, the principle that we couldn't use more cranberry juice than we had available. But there's also a constraint on the amount of apple juice available. If we repeat the steps I went through with the Cartesian plane, we'd get a graph like this. Again, we have regions which require more apple juice than we own, and regions where apple juice would be left over. The boundary line represents using exactly the 100 quart supply of apple juice we have. In this case, the equation for the line is x plus 2y equals 100. Keeping our recipes in mind, this equation represents that we need to include 1 quart of apple to make 1 gallon of cran-apple juice, or X, and we need 2 quarts of apple to make 1 gallon of appleberry juice, or Y. We figured out some important information about each of the pieces. What happens when we put it all together? We want to apply all the constraints at once. The fact that we can't use more cranberry juice than we have, the fact that we can't use more apple juice than we have, and the fact that we can't make any negative quantities. Well, that amounts to putting both of the lines that I developed separately onto the same picture, the same coordinate system, and seeing where the feasible regions overlap. You can see that the lines have now divided the positive part of the plane into 4 areas. This upper region includes points which aren't feasible because you wouldn't have enough of either kind of juice. In this wedge, we'd have enough cranberry juice, but not enough apple juice. The reverse is true down in this wedge. Here, between these lines, we're talking about having enough of both juices. Now, if we zoom in a bit on the feasible region, we can identify 4 corner points. What's more, we can label each of them with their Cartesian coordinates. 2 of these 4 points have coordinates that we had to compute in order to draw the line in the first place. Our third point is labeled 0, 0, and we know that because it's at the cross point of the axes. But figuring the coordinates of the 4th point again entails a bit of algebra. The technique in a nutshell is to take the equations for the 2 lines and solve them simultaneously. I don't want to veer off on that, so I'll just give you the results. Voila, the feasible region we've been after. But there is one drawback. This region contains an infinite number of feasible points. Now you can decide without any prompting from me that some of these points may not represent such great production policies. The point 0, 0, for example, doesn't sound like it's going to make much money because it's not going to make any juice. But we're still confronted with a lot of possibilities. In fact, although we seem to be closer to a solution, there is still an infinite number of feasible points in our diagram. An important discovery about linear programming problems is that there is a principle that can help us narrow our search, the corner principle. This principle says that the best profit will be at some corner. In this case, we only have 4 corners, so the answer should be in striking distance. The way we proceed now is to take our profit formula and compute the profit for each corner by plugging in the numbers one at a time. That formula, remember, was profit equals 3x plus 4y. We've already eliminated the 0, 0 corner. As I step through the other corners, we can store the results of each profit calculation next to the corner coordinates. From the calculations, we see that 250 is the highest profit, and it occurs at precisely this point. And thanks to the corner principle, I don't have to test any other points, whether they're on the lines or in the yellow region. The corner coordinates are the only ones that are in competition. The corner principle is pretty powerful, but I don't want to leave you thinking that it's magical, just pulled somehow out of a hat. It's a consequence of our profit formula, 3x plus 4y, or rather I should say of the kind of linear equation that our profit formula represents. On the graph, I've drawn a line that represents an arbitrary profit of 150. It crosses the feasible region, so all the points on it represent production policies that we could carry out. But clearly, this is not the maximum possible profit. I'll let the profit line inch up the graph. Each time the line moves, the profit it represents is also inching up, from 150 to 151, 152, and so on. If the line moves so far up that it no longer touches the feasible region, then the value it represents is no good. Now, the corner principle simply observes that at the instant when you're just about to kiss the feasible region goodbye, you must be touching that region at one point at least, that is, at one corner point. Let's not lose sight of the fact that we got our answer. The coordinates of that best corner, 5025, give us the production policy that yields the highest profit. So turning a real-world problem into a set of linear equations requires a thorough understanding of the ideas we started with: production policy, constraints, and optimization. And plugging our mathematics back into reality, we find that the optimal solution to our juicy problem is this. Our production policy should be to make 50 gallons of cranapple and 25 gallons of appleberry for a total profit of $2.50. The corner principle was easy to apply in our example, but that's not always the case. It's conceivable you could have a weirdly shaped feasible region and therefore a lot of corners to deal with. And a lot of corners means a lot of computation. Not difficult in theory, but it can mean substantial difficulty with the method in practice. There's another difficulty, something a little more exotic. In our example, the feasible region was two-dimensional, easy to visualize and easy to graph. But it can happen that the problem requires 3 dimensions, or even more. If it's more than 3, you can't even visualize what the feasible region might look like. How can you tackle a problem like that? You'll be glad to know that there is a method for this situation, a linear programming technique called the simplex method. The problem of visualizing higher dimensions just disappears because the simplex method is completely algebraic. No need for a geometric picture. But just to get the idea, imagine a feasible region that's a polyhedron with many corners. The first step in the simplex method is like the beginning of a card trick. Pick a corner, any corner. It really doesn't matter where you start, because the simplex method is a procedure for getting from one corner to a neighboring corner whose value is closer to the optimal solution. By neighbor, I mean a corner that you can get to from the corner you're on by walking along an edge of this polyhedron. The yellow corner and our original corner are neighbors. The red one is not, because even though it seems closer, we can't get there by walking along just one edge. From any one corner, like the one we chose, the algebra of the simplex method allows you to compute from the corner you're already on which neighbor you should try next, which one moves you in the right direction, so to speak. In our example, the computations would lead from our original corner to this neighbor, then from there to a neighbor of that corner, and so on, until you reach the point that's marked as optimal. So there are a lot of corners you never have to bother to visit, and therefore a lot of calculations you don't have to perform. When the simplex method is used, it visits a very small fraction of the corners, and so it's usually a very efficient way of solving linear programming problems. For the past 40 years, the simplex method has been working mathematical miracles for industries worldwide, saving both time and money. And what industry does can have a pretty direct effect on you and me, the consumers. But at this point, you must be wondering how such a sophisticated computational technique translates into real-life, everyday applications. May I help you? Yeah, can I get a hot dog and a soda?
Sure, $2.
Thanks. What could be more real life than driving to your local hot dog stand? In procuring my lunch, I've been touched by no fewer than 3 simplex method solutions to linear programming problems.
Thank you, sir. Have a nice day.
Thank you. First, there's my car. Computers at General Motors apply the simplex method all the time. After all, GM manufactures 60 models of passenger cars and trucks every year. Now, the sales from some of those models are more profitable to GM than others. But as we learned in our juice example, it isn't always good business to produce only your highest profit maker. So in order to create the best production policy, GM has to consider a lot of variables, like choosing which body styles and which new car features to offer their customers. Obviously, there are many other possible product mixes to consider as well. Attempting to study all of the combinations would take centuries, and by then, cars would be obsolete. And then there's the oil that fuels my car. And oil refineries don't stop at making motor oils. Ink, aspirin, guitar strings, hair coloring, perfume, insect repellent, ping pong paddles, deodorants, carpeting, and even bubble gum are just a few of the 3,000 possible petroleum products. So again, we run into the problem of trying to visualize a feasible region for all possible product combinations. If each of our possible petroleum products is represented by a dimension in space, we need 3,000 dimensions in order to draw a picture. Well, all these examples have made me pretty confused and hungry. And that reminds me of our third example, my lunch. On any given day, the ingredients in my hot dog may change. One week it could be mostly beef. Another week it might contain mostly pork. These changes are directly related to the current price of the ingredient meats and how much money our hot dog manufacturer expects as profit. These decisions are made using the simplex method to determine the production policy that yields the highest profit, given the constraints of the business. But mathematicians are never content to assume that just because a method works very well, it's the last word on how to tackle a problem. Very recently, in fact, after years of research, there's been a mathematical development which may improve the efficiency of linear programming. Narendra Karmakar, a young mathematician at Bell Labs, has devised a new procedure for handling very complex linear programming problems. If you imagine the polyhedron we looked at earlier, Dr. Karmakar's method is to start in the center rather than some outside corner. Each time a point is chosen closer to the optimum point, the axes of the polyhedron are stretched in such a way that our new point is now in the center. Theoretically, this process allows you to locate the optimal point with fewer calculations.
As the problems become large and complex, the simplex algorithm takes much longer to solve these, as opposed to the new method, which will be able to handle even larger problems. There are some users who have already started using it, such as internally within AT&T. But then many people have to be trained to to understand and use the new methods, and therefore it will take quite some years before it comes into full-fledged application.
Bell Labs supports a lot of pure mathematical research, and that's Dr. Karmakar's field. But the potential applications of his method are very important to many large businesses, including AT&T. Routing millions of long-distance phone calls is a resource allocation problem. How to use long-distance landlines, repeater amplifiers, and satellite terminals to the best possible advantage. Flight crew schedules and aircraft fuel loads are other examples of resource allocation problems. American Airlines is one of the companies interested in Dr. Karmakar's technique to see whether it can help cut costs. Thomas Cook is Director of Operations for American.
If indeed we can get an algorithm that is 50 to 100 times faster than existing technology, we can do a lot of things with that algorithm that we couldn't do today. A good example of that kind of an application is what we call a major weather disruption. If we get a major weather disruption at one of our hubs, like Dallas or Chicago, and a lot of flights get canceled, and we have a lot of crews, a lot of airplanes in the wrong places. And what we need is a way of putting that whole thing back together again so that the crews are in the right place, the airplanes are in the right places, and we minimize the cost of that disruption and minimize the passenger inconvenience of that disruption. Well, we're working on that problem today, but in order to solve that problem in an optimal fashion, we need something as fast as Karmakar's algorithm to do it. So in the absence of Karmakar's algorithm, we'll have to come up with some heuristic kinds of ways of solving that problem that won't be optimal.
You might notice something familiar in those two possible applications for Dr. Karmakar's theoretical breakthrough in linear programming. Long-distance telephone routing and flight crew scheduling were two of the situations we looked at earlier when we were talking about routing algorithms. That brings me to my final point. One of the things that's so important about linear programming in both theoretical mathematics and practical applications is the way it unifies kinds of problems that we used to see as distinct. We saw earlier that there was some resemblance between the traveling salesman problem and the bin packing problem, between routing and scheduling. It turns out that these topics, along with street networks and resource allocation, are all pieces of a larger jigsaw puzzle. It's linear programming that allows us to see that puzzle as a unified whole. Each of these specialized problems can be described by a set of equations and inequalities that fall into the linear programming category. And that category, that unified set of problems, is a fairly large portion of what today makes up the subject of management science. It's no exaggeration to say that if it were not for the development of linear programming, the whole idea of management science as a single subject might not have developed. And because, as we've seen, linear programming techniques continue to evolve, management science is becoming more and more effective and important.